In this example, we will solve a single slope tapered section type structure with a column in the middle. We start by choosing a new project. New project. I choose type 520. Total truss span is 40 meters. Column heights are 7.5 meters. Let the axis distances be 6 meters. The distance between purlins are very high right now. Let's change it from the features of our truss. Keep the roof slope around 6%. The distance between the purlins is 3.34 meters, which is very high. I'm reducing it. I'll try to make it around 1.5 meters. DCY is the initial height of the first beam over there. Initial height is 0.8 meters. DCX is the width at the top end of the column. 0.8 meters. Let it be 0.8 meters. DMY is the distance of the middle column from its top point, 0.7 meters. I also changed the DRY value to 0.8 meters like the column on the side. Let the NDCX reinforced section in the corner continue for 4 purlins. NDRX is the variable section on the ridge. That section. Let it continue for 4 purlins. In the middle, along the 2 purlins, to the right and to the left. Let that get bigger too. Let this place stay for a purlin. We have a structure like this. Let's increase the number of axes so that the length of this structure is 60 meters. IS 875 is chosen as the load standard because this structure is in India. Let's use American regulations this time, AISC 360-16. Let's enter loading parameters. Our roof cladding is sandwich panel. Let's have solar panels on the right and left of our roof. There is only one left slope here. That's 20 kilos per square meter. As a snow load, I take it very little considering that this place is in India. By thinking of the rain, our structure is in the red zone over there. That's why 55 meters per second, no internal pressure. We are constructing this building in a category 4, in a city zone. The area where our building is. Over there. In zone 3. I think it was made somewhere around here, in a yellow area. Our soil class for a bad ground. Our structure type is ordinary moment resisting frame. The purpose of our building. Keep it as 0.5 for now, I haven't changed it. It doesn't matter since we won't define a mezzanine anyway. Let's check the loads coming to our structure according to this information. Snow loads on the roof. Wind from the left. Wind from right. And the wind from behind. When the wind comes from the front. MK PEB can automatically transfer them onto secondary structure elements. From there to the main carrier system. After we see how the loads are transferred, let's calculate our roof purlins. Our roof purlins work in 83% capacity according to wind loads. It's upwards. Let the C220 stay. Our girts that are under the wall cladding. Our girts are at 51% capacity so we can lower them a bit. YZA is the left column. YZB is the right column. Let's check it in the right column. There are probably more girts here. That's why it came this way. Are left and right different? Yes, as 6 and 7. Then the sections of our main columns. Our main columns. The left and the right column. Put the circle on the selected column. Flange width 140 by 10. I chose the profile with a body of 8 mm and a height of 400 mm. Steel grade S235. I have closed the side columns. Middle column. There is no cladding on the middle columns. I don't want too many varieties. 140 by 10. A 300 mm high column. S235 steel quality. Our beam sections are 140 by 10, I still choose the same profiles. 400 to 8. It's half as high as I've chosen the height over there. Let's start a static calculation according to what we have chosen and check the adequacy of our sections. When we look at here, the deflections are very low, but the sections are not enough. This is due to lateral buckling. Such a lateral buckling length is quite effective in the AISC 360/16. That's why I add lateral supports from the model part, one, by skipping. Let's see where we added here. Not this, here. It's as if they are symmetrical. I repeat the static calculation. Our rods are at 60% capacity. There is no problem with our stability beams. Enlarging the section is an alternative here. We can also add lateral support to the columns. Let's consider adding lateral support to the columns. For this, I mark the wall purlins as having lateral supports. Then these signs appear. Then I did the same thing to the other column on the side. And then I repeat the analysis. At the moment, all of our sections seem sufficient. At this stage, let's add wind columns to this structure. Wind columns. First truss. Let's take a look over here. There is a column at 20 meters. I try to be symmetrical like this. We have wind columns at 4, 8, 18 and 22. We have wind columns at 4, 8, 18 and 22. When we define wind columns, the placement of the roof braces is changed automatically. It would be nicer if we made that gap wider. Let's change it that way. 17 and 9. This is how our program placed the braces. Now let's repeat the static analysis. Our braces had a lower capacity ratio a little while ago, now they have increased a little more. Let's look at the other axis. On the other axis, our rods are sufficient too. The reason it comes out this way is the wind loads coming from the front and back. At the moment, our wind columns are insufficient. Only they seem to have a problem. On the front shield axis, I chose the main beams. I switched to intermediate axes. I want to assign a higher rafter on intermediate axes. Let the height be 500 mm this time. I repeat the static analysis. I looked at the XZ axle. We have increased the height of the beams. This was a good solution. Now I will choose the sections of our columns from the same sections. Main columns. 26 and 28. Like this 500 to 8. We forgot to change the section of the wind columns. We found that these were insufficient. Let's make these again from the same beams. I choose 500 to 8 same sections. These wind columns shall not be of tapered section. Now I repeat the analysis. Now our wind columns are also sufficient. I switched to intermediate axes. I looked. All of our sections seem to be complete with everything. In this example, there was braces at the beginning and at the end, and 2 in the middle. Let me show you another feature of MK PEB. We choose the placement of the roof braces at the beginning and at the end, but we have a second method. When we use this method, we can decide the locations of the braces by ourselves. No braces at the beginning and at the end. Braces are on the second and second to last. There's also one in between. So I repeated the analysis. The number of braces has now decreased by 1. As we can see, 3 braces are enough with 20 mm rods. We have seen before that other axes are sufficient. We could have achieved a better result if we enlarged the rods a little on the YZB, that is, the middle axis. In the rightmost C-axis, the sections are sufficient. Let's change the rods on the middle axle braces. Let these be 24 rods, not 20 rods. Those on the other axes remained as 20 mm rods. We now repeat the analysis. Our middle braces. The 24 mm rods of the YZB axle are much better than the previous 20 mm rods. We forgot the calculation of the braces on the roof. Let's check them out. Roof braces in second building elements. Let's look at our building model and try to see which braces are forced. Now, from this page, it can actually calculate according to front wind, rear wind and earthquake loads. There is a problem with those braces. What braces are these? Braces on first and last axle. Because they take the wind loads. Then I changed the first and last braces. I also made them 24. 24 is a little bit within the limits. We can think of a bigger one. Or we can say enough and stay within the limits. I also replaced those 20 rods with 24 rods to avoid variety. From this page we can access the detailed report of the calculations. Here is the calculation of the 24 rods. We calculate according to AISC 360-16. Their only tension member. Although at the limits, the sections are sufficient for now. Now, after this stage, we did not calculate any connections. In order to design the connections, static analysis must be done. In this project, I plan to calculate only the intermediate axles of the XZ2 axis and the inside of this axis. In a normal project, you have to do it all. Connection analysis, these are our intermediate axles. 0 and 10 were the front and back shield axes. In this example, we will make the beam bolted connection placed on the column. We will show how we do side connection in another project in detail. Let's see why it didn't work. There is a problem with the moment resistance. The cause of the moment resistance problem is usually due to that plate thickness. I made the plate thickness 20 mm. Now it's sufficient. Is there an uncomfortable thickness or any problem in the connection? No, there isn't. We put the following connection plates in between, without considering them in the calculation. There is a stiffener plate for preventing panel buckling. It was meant to be done as a precaution. In order not to control the panel buckling calculation on the panel, we preferred to put the plate here automatically. Now, as the symmetry of this, I move to the other side of the building. We take the values from 0R to make quick calculations. Our 20 mm plates have arrived. Let's look at the results. Even if the results are 92%, they are sufficient for now. It says load combination number 32. The load combination number 32 is most forced under the following combination. I saved it. Then there are splices in the areas where the cross-section changed. Let's check our beam splice connections. There is also moment resistance problem in splices, and we see that welds are forced a bit. I made the plate 15 so that it would not be of different types and put another row of bolts in the middle. I put it in third place. It's sufficient now. It's sufficient. No, I save this too. Saved as 4R. I got the values from 4R for the next connection. I looked at the results. The results are sufficient again. There was a colon in between. Now let's calculate the column beam top connection. Let's fix the plate used in the connection here first. I changed it to 300. I changed it to 150 here. I put 3 rows of bolts in it. Like this. I checked the calculations. The program says there is a problem with the weld resistance. There's a problem with the welds between the column and the plate over there. Let's look at the weld thicknesses. Our weld thicknesses are very thin. Let's change them to 5 mm. In this connection, we could do the following to pull the edge distances over there. We can increment EY1 and EY2. For example, let's do these 50. Let them come a little more towards the middle. Let's check the calculations. No problem. Then let's see if there is the same connection elsewhere. No, there isn't. We're on other splices now. The 4R was our splice. The one with 3 bolts. Let's look at the results. Weld thicknesses are within limits. Of course, we should not stay within such limits. Could it have been done better? It would be better if we increased the weld thickness a little bit. This is how we completed our connections. Now let's redraw our construction model. Our splices have arrived, our other column beam splices have arrived. We have now calculated the connections of this axis. Now let's come to the column base. These column bases are rigid. We can solve it together with foundations. When we look at it, it seems like the plate is a little narrow. Let's enlarge this plate first. I changed the width of the plate to 400 mm, height to 650 mm and thickness to 20 mm. Here's how the column base looks. Let's put a row of bolts in the middle. Let our anchors be 24 mm. Let's have a look at the results here. What level are we at? The thickness of the column base is sufficient. There is no problem in the bearing capacity of the foundation. And the reinforcements of only our pad foundations are insufficient. Let's fix them. Pad foundations. Reinforcement of pad foundations. I increased the reinforcement count. I want it under 20 centimeters. I also increased these to around 20 centimeters. I looked at the results. Longitudinal reinforcement seems insufficient. Instead of increasing the number, I increased the diameter. Now it's sufficient. I took a quick look at the column base plate and footing design. The height of the flag plate seemed a little too high. I reduced the height of the flag plate. MK PEB does not take into account the flag plates on the column base plate connection analysis. We could do it like this. It wouldn't change the result. But I would still prefer to have two flag plates like this. I also saved this connection. Now we come to the middle columns. This section of the middle column could be smaller than the others. But I don't want too much variety. Sufficient. Right column. Although it is within the limits of 93.5%, it is sufficient. Same load combination 6, due to snow loading, the thickness of the column base plate is too much. It was forced over there mostly. Let's save the changes and redraw. In this way, we can also perform connection calculations. Similarly, I had to do it for other axles, but since this is an example project, I will not continue until the end. Now let's review the cost of our construction again. Currently, the amount of steel used per square meter is around 29 kilograms. Let's take a three-dimensional model of our structure. Our drawing has arrived. Let's take a closer look at what we have added to our model. Our connection calculations have arrived, our purlin supports have arrived. To prevent lateral buckling, beam lateral supports came. We used lateral supports on the columns, we can see them too. Our connections with 3 bolts have arrived. We did not calculate these. Similarly, our intermediate columns have arrived. Our roof braces and their connections have arrived. Our column base and foundations are visible. In this way, we have obtained a 3D model of our structure. After this step, we do the part numbering. After enumerating, the real cost of the building can be calculated here for the first time. The previous ones were approximate cost analysis. Now let's look at the actual cost analysis. 29.58 kilograms per square meter. Our next step is to obtain the technical drawings. Let's get our plans first. Our plans have arrived. Column layout. Anchor details. Those 3 belong to the first axle. It belongs to the front axle. That's the column foot of the axis we calculated. That's our foundation plan. Our roof layout plan at the top chord level. Here are the parts numbers. And here we have given the details of the parts as a table. And the cross-section of the building at the front shield. Now let's move on to our second drawings. Cross-sections. Cross-section of the 1-to-1 axis. Let's not take the connection details because we didn't calculate it. We calculated the connection details of the 2-to-2 axis, let's take all of them. Our drawings have arrived. Front shield axis, 1-to-1 axis. Values represent the profiles used, this is the starter profile. Values represent the profiles used, this is the starter profile. C2 is the assembly part number. Intermediate axles, 2-to-2 axle. Connection details have numbers. Similarly, these are the splice connections detail numbers. Similarly, here is the number of the splices in the column beam connection. Left column beam connection. Additional details and splices. Dimensions and thicknesses of welds. In this way, it can extract the details of the connections. And on the right you can find the drawing of those 3 pad foundations. I'm closing them now. Reaction forces. Sometimes they position the columns of these buildings on spread foundations, then reaction forces are required. Reaction forces were possible to show as a table, but we wanted to give them as a drawing too. Here are the numbers of support reactions. And according to the load combinations, we can see the incoming reaction forces at 27, 28 and 29 from here. Let's look at the drawings of the assembly parts. Let's take the drawings of the assembly part of the B1 and C1 column. This is our beam. The names of the parts used in our beam. Information on which piece to use in which quantity. Detail over there is the detail on the column beam connection. 3-dimensional view of the assembly part. And we can follow the dimensions of the parts that make up the assembly part here. Similarly, let's look at the column. This is our column. The individual parts that are build-up column. Sectional view taken from here at the top end of the column. 3-dimensional view of the column base plate connection. And here we have the chance to see the list of individual parts that the build-up column. This is how we can get the connection details in the assembly part drawings.